Okay, good evening everyone. I'm Shivani Tok and I welcome you all for the week 7 tutorial session for the course of digital signal processing and its application. So like every week I'll first discuss whatever concepts were or just quickly skim through the concepts that were discussed in this week, and after that we'll solve few questions which are related to the content. So let's start with the recap. So this week basically we started with designing filters. So what we saw that if we look at ideal filters, then the ideal filters are neither causal or they can't be made causal. They are not stable and they are not realizable. And therefore, we need to go for some sort of compromises in ideal filters so that we can have realizable filters and somehow we are able to make them causal, something like that. So the compromises that we need to do with ideal filter is we can't have a constant passband or stop band frequency, stop band magnitudes. We need some tolerances in that. Another thing is we require a transition band. So basically we can't have a discontinuity between the passband and stop band. We need a smooth transition from passband to to stop band, which will generate a transition band. And for realizable filter, we can't make this transition band as 0. And for filter design, so what basically we mean by filter design is we want to find a rational approximation for this ideal filter. So basically we want to have rational filters which will be definitely realizable, and these rational filters should approximate to certain extent to the ideal filters which we have seen in the previous week. So the very initial approach that was thought of in digital signal processing is we know the entire history of analog filter designing. We know how the filters are being designed for analog signal processing. So why not mimic the same thing for discrete filter, or whatever available thing we have for analog filters, somehow try to convert it to a discrete filter. And when we want to convert it to a discrete filter, then we want to preserve its stability. We need to preserve the nature of filter, that is a low pass filter. A low pass filter should give me a low pass filter. Similarly, a high pass should give a high pass, and so on. And another thing is we want this to be a monotonically increasing sinusoidal frequency. That is, we have this omega in analog domain and we have this small omega in discrete domain. So these should be related in with a monotonically increasing function, and it should be a one-to-one function. And one such transform which helps us in doing this is this bilinear transform, where this bilinear transform is given by S is equal to 1 minus Z inverse upon 1 plus Z inverse, and this satisfies all the properties which are there in this. Then we looked at the basic steps of IIR filter designing. So the very first step is we need to normalize the specifications. So basically the specifications will be given to us in hertz frequency. That is, if a person comes to you, you being a designer, he will tell you that I want a filter. Let's say it wants us to process our voice signal, which can have maximum value of 3.5 kilohertz. So he wants a filter that will pass only my voice signal. Let's say it has a cutoff frequency of 4 kilohertz. And so it will give you a pass band edge, it will give you a stop band edge in hertz frequency. Now that hertz frequency you need to convert into its respective discrete domain frequency. That is, you want to convert this omega, capital omega, to small omega. After that you need to perform a bilinear transform to get capital omega from small omega. So this thing we are doing so that, so if you observe carefully, we had found out that this omega is tan of omega by 2. And if you observe carefully, this is not a linear function of omega. There is a non-linearity that is coming up. And therefore, this omega which we had here, which we got from hertz frequency, will take you to small omega. And when you apply this formula here, you won't get the same thing which was obtained here. That we'll try to see in some example, maybe in coming week or somehow. So we need to get omega by doing bilinear transform, by applying this formula which I mentioned here, which is omega equal to tan of omega by 2. Here we want to get omega, which is 2 pi f by fs, where fs is sampling frequency. After that, we have this omega here, and then we need to find the analog filter. And after doing analog filter, we want to do bilinear transform. So here I mean. So this will be S equal to 1 minus Z inverse upon 1 plus Z inverse. You need to substitute this in the given transfer function or whatever transfer function we had obtained using these frequencies, these set of frequencies and other parameters. And the very first approach with which we started was Butterworth filter. So we'll take one example for Butterworth filter just to understand. This Butterworth filter will be continued in coming week also with more detailed things. So this was all that was covered in this week. If you have any queries in this content, please let me know. Otherwise, I'll start with the questions. Okay, if there are no questions, then let me start with the questions that I have planned to cover today. So this is the first question. So what does it say? Which statement is correct for the following transform? So this is the transform which is given to us where S is equal to log Z. And we need to assume that the imaginary part of this log of Z will belong to minus pi to pi. And this is a multiple answer correct question. So each of these points we'll try to understand one by one. So let us try to understand this transform first. What exactly is happening here? Okay, so the transform given to us is S equal to log Z. And I can write this Z as A into e power j omega, where magnitude of Z is equal to A and angle of Z is equal to omega. Okay, and this omega, okay, so this we know here, and then this S is equal to log of A e power j omega, which I can write as log of A plus j omega. So the transform which is given to us is S equal to log of A plus j omega, and what is given to us is imaginary part of S which is equal to omega. This belongs to a range of minus pi to pi. Okay, so this we have. Now let us look at these points one by one. So let me just take this and I'll add the same template. Okay. So this we have. Now let us consider the very first point which we have. So it says that mapping is one-to-one mapping from Z domain to S domain. So now if you look at this transform, the very initial statement that was given to us, so it was S equal to log Z. You can write this as Z equal to e power S, which means that we have the existence of invertible function or inverse. And if this kind of inverse exists, which means that this is one-to-one mapping. So, which means that the first option is correct. Okay. So basically this is a multiple answer correct question. So we need to check all the possibilities that we are having here. The second point here is each circle in Z plane is mapped to an infinite line in S plane. Okay, so now just look at this transform which we had seen. So this was log of A plus j times omega. Okay, now this infinite line uh, with respect to its j omega axis or imaginary axis. Okay, so now if you observe carefully, we have this. This is, let's say, my sigma, and this is my j omega. So this is my sigma axis and this is my j omega axis. And infinite thing means 1z should correspond to an infinite axis. That means this omega should vary from minus infinity to infinity. This, if this happens, then we mean that we have an infinite line. But what is given to us? We have this omega, which is basically imaginary part of log of z. This belongs to minus pi to pi. That is, let's say this is pi and this is minus pi. So all the possible lines, or rather if I specifically say, whatever we are having here, this transform is only covering this region. Okay, and it will have lines which will be of this form, like this, from minus pi to pi. So this will be log of a1, this will be log of a2, so we'll have another line and so on, like this we'll have. So instead of getting a line, what we will get is line segments. Which means that this thing here, that each circle in z plane, so how will I get a circle? I'll have to vary this thing. For varying the radius, I'll have to vary the value of a, and in order to rotate it, I'll have to vary my omega. So when I am varying my omega, this is just from minus pi to pi, but this can take any value from minus infinity to this a can take any value from 0 to infinity, and since this is a log function, it can take any value from minus infinity to infinity. Okay, so this region it will cover, but there won't be anything in this region. And instead of lines which are of infinite length, I'll have line segments. Okay, so therefore each circle in z plane is not mapped to an infinite line in s plane. So the second option is wrong. Okay, now let us look at the third option. What does it say? The interior of mod z equal to 1 is mapped to the subset of the region real part of s is less than 0. Okay, so now what we have considered, my z is equal to a e power j omega, which means that mod of z is equal to a, and interior of uh, interior of mod of z equal to 1, which means that we need to take region which is mod of z which is equal to a less than 1. Now the transform that we have, what do we have? We have this s as log of a plus j omega, and real part of s is log of a. So what do we have? We have a less than 1 and real part of s is equal to log a, And for all the values of a which are less than 1, log of a will give me negative value. So this will be less than 0. So what does it mean? If we have mod of z less than 1, then we will have a region which is subset of the case where real part of S is less than 0. So this means that this third option is correct. This option is correct. Okay. And what is the last option? The entire S-plane is covered by the transform. So that you can see from this figure itself. So let me number this. Let's say this is figure 1. So from figure 1 you can see that only this part is covered. Anything which is here and here is not covered, which means that it's not covering my entire S-plane. Why? Because my omega, this omega is just varying from minus pi to pi. If this would have varied from minus infinity to infinity, then yes, this particular thing will also cover the entire S-plane. But for this particular given case, when my omega is varying from minus pi to pi, it is not covering my entire plane. So this option is wrong. So let me write it down. For fourth option, since omega belongs to minus pi to pi, S equal to log of A plus j omega do not cover the entire S-plane. So see figure 1. So therefore my option 4 is wrong. So what are the two correct options? So we had seen that this option was correct and this option was correct. So 1 and 3 are the correct answers. The second option and the fourth option are wrong. So our final answer will be option number 1 and option number 3. Any questions? Is this clear? Is this question clear?
Yes, madam.
Okay. Okay, if this question is clear, then let's move on to the next question. So this question here is we have this Z plane and we need to map these points, which is A, B, C and D. We need to map these points to the S plane. Okay, so we have these points given here and this dotted line is basically our unit circle. So this thing here is unit circle. So anytime when you are given a Z plane and you are given a dotted circle or any kind of circle, if it is given to you, you can safely assume that it is a unit circle unless and until somewhere the radius is mentioned. So, and another thing that I forgot to mention here is you need to consider bilinear transform. Okay, so this mapping has to be done with bilinear transform. Okay, so now let us do it. So now you observe carefully this thing here, we are in r comma omega plane, that is polar plane, and here this thing is sigma and this thing is omega. Now when we are considering bilinear transform, unit circle will correspond to j omega axis, which means that A, B, C, and D all lie on j omega axis. This is the first thing that we can see. Now, what is bilinear transform? Bilinear transform is S equal to 1 minus Z inverse upon 1 plus Z inverse. And since we are on the unit circle, this thing I can write as j omega is equal to 1 minus e power minus j omega upon 1 plus e power minus j omega. This comes out to be j times tan of omega by 2. This we had solved in the lecture. If you want, I can simplify this further. Please let me know. And this thing here, what does it tell us? My omega is tan of omega by 2. Okay, so this we know here. Okay. So what does this tell us? Based on the angle at which all these points are located, based on the angles of these points located, I can get a value corresponding to this capital omega. Okay, so let me draw S plane here. This is sigma, this is j omega, and the first thing that we are having here is, let's start with point A. So let's start with A. How much angle does A make with positive real axis? So it is this 180 degree. Okay, this is 180 degree. So this we have as, for point A, omega is tan of pi by 2, where the small omega is pi or 180 degrees, and this thing here is equal to infinity. Right, so my point A will lie somewhere here where this tends to infinity. Right, this will be at infinity. Next point that we are having is, let me just change this color to a red so that we can have track of things. Next, let us look at B. Where is my point B? So this is B, and B is located on the positive real axis. So this particular point makes an angle 0. So for this, small omega is 0. So this we have omega equal to tan of 0, which is equal to 0. So this B will lie here. That is at omega equal to 0. Now let us look at C. Where is my C? The C is located here, and this makes an angle of 60 degrees. Okay, so this thing we have C. This makes an angle of 60 degrees. So this will be tan of 60 by 2 in degrees, which is equal to tan of 30 degrees. So this thing here will come out to be as 1 by root 3. So if this is 1 by root 3, this is greater than 0, and therefore this will lie somewhere here. So point C will lie somewhere here. Okay, and now let us look at where my D is. So my D lies here. So this thing is 180 plus 30. This is 30 degrees. Or you can say 2 pi minus 60 degrees. So this thing D, point D, is omega equal to tan of 2 pi is 360 minus 120 by 2, and this thing here,
minus 150 no, madam.
yeah, sorry, 150, not 120. Yeah, sorry, thanks. Minus 150 by 2, and this thing will have a value which is greater than pi. This is lying in this third quadrant. It is having a higher angle, so this thing will be having a negative value, and this thing will lie somewhere here. Okay, another trick that you can, so this is the way we are having, that is A, C, D, and A, C, B, and D. Another trick that you can do here is, let me just take this thing, or let me add page of same template and shift it there. So this was one approach that we can do. Another approach that we can do is, we have omega as tan of omega by 2, and in the range of minus pi to pi, this thing is, this thing here is monotonic function of omega, or rather monotonically increasing function of omega. So now if you observe here, angle of B is less than angle of C, is less than angle of, write it properly, is less than angle of C, is less than angle of A, is less than angle of D. Okay, which means that omega corresponding to B will be least. Sorry, this D will come before. We need to look from minus pi to pi. So from here we need to see in this direction. Yeah. So angle of D is less than angle of B, is less than angle of C, is less than angle of A, which means that this D point will have, the omega corresponding to this point D will be least. So if you look at that, the only possible options are this A, B, and D. Then, so yeah, like this. So omega corresponding, then omega corresponding to B will be higher than that for D. So then if you compare, then we have that in this plot. It's not there in this plot, it's not there in this plot. Another thing is, then omega corresponding to C will be higher than that of B. So this also we are having, and omega corresponding to A is higher than what we are having. Now if you compare, this is the same thing that we had seen earlier. So D was below B, B was below C, and C was below A. So this is the exact same plot, which is option A, that is A, C, B, D. Here also we are having A, C, B, and D. So this is the answer to our question. Any doubts in this part? Any queries here? Okay. If there are no queries, then sorry.
Hello, madam.
Yes.
You wrote x is equal to 1 minus z power minus 1 by 1 plus z power minus 1
Yes.
by linear transform. In place of 1, if there is 2,
Huh.
you want to know what happened. In
Like
place of 1, there is 2.
1
2.
minus z to the power minus 2 or 2 minus z to the power
2
minus
minus 2 minus z power minus 1 by 2 plus z power.
Okay, I'll suggest you to check if the magnitude thing is 1 or not. Magnitude of z should come out to be 1.
It must be 1.
For when you're setting S as j omega.
Okay.
Yeah. Something there will be a mismatch. You can try doing it.
Yeah. Okay.
Just check out all the things that we require in this particular transform, in bilinear transform.
So,
Or what you can do is, this is a bilinear transform, right? A minus bz inverse upon a plus bz inverse. Just try to do it and
okay.
find the conditions that you need on a and b. So that will be a good exercise to see.
Okay.
Yeah. Okay. Any other questions? Okay. If there are no questions, then let me move on to the next question. So this is the question number 3, and what it says is, consider the transform S equal to 1 minus z to the power minus 2 upon 1 plus z to the power minus 2 and corresponding frequency transform from continuous time frequency omega to discrete time filter frequency small omega. Which of the following statements is are correct? This is also multiple answer correct question, and we need to see what exactly is happening in this particular thing. Okay. Okay, so let's start with this. So what we have here is S is equal to 1 minus z to the power minus 2 upon 1 plus z to the power minus 2. Okay, now what I'll do is, we have this in this particular form. Yeah, so what I can do here is, so this thing I can write as sigma plus j omega. Okay, and let's do this. Then we can write z as magnitude of z, which is r into e power minus j omega. So this I can write as 1 minus r into e power minus j2 omega upon 1 plus r into e power.
Madam, it is r square, no? R square.
Okay, this we are having. Then what we can do is, we can write this as 1 minus r square into cos of 2 omega minus j times sine of 2 omega upon 1 plus r square cos of 2 omega plus j times sine of 2 omega.
Ma'am,
Yeah,
ma'am, Z is equal to R e power j omega, no?
yeah,
So
Then
r
whole
power
correct.
minus 2. R power minus 2.
this is z to the power minus 2.
Z will be replaced with e power
Z is e
r
power
g,
r into e power j omega. So
then
I can
whole to
write
the
this
power.
as r into e power j omega to the power minus 2.
Yeah, yes. We are writing here plus 2.
Yeah, sorry, thanks. Yeah, thanks. Yeah, will be r to the power minus 2. Thank you. Okay, so this I can write as 1 minus r to the power minus 2 cos of 2 omega plus j times r to the power minus 2 sine of 2 omega upon 1 minus r to the power minus 2, sorry, plus cos of 2 omega plus j times r to the power minus 2 sine of 2 omega. And let us make magnitude of this quantity as let's try to make this as a non-complex quantity. So for that I'll have to multiply by the complex conjugate. So the below term is just, so if this thing is, let's say, a, then I'll multiply this by a bar and multiply this by a bar as well. So let us now just focus on this numerator part. So this thing I'll focus because that's the only complex thing that we are having. Okay, so let us consider this thing here. So what we will have, 1 minus r to the power minus 2 cos of 2 omega plus j times r to the power minus 2 sine of 2 omega multiplied by 1 plus r to the power minus 2 cos of 2 omega minus j times r to the power minus 2 sine of 2 omega. And this thing will give me 1 minus r to the power minus 4 cos square 2 omega plus j r to the power minus 2. So if I just look at real part of this quantity, then this will be this thing multiplied by this thing. If this thing gets multiplied by this thing, it will be imaginary. If this thing gets multiplied with this thing, it will be imaginary. So the cross terms will give me imaginary thing, and this thing multiplied by this thing will give me a real quantity. So then I'll have plus r to the power minus 4 sine of sine square 2 omega. So what I have is this as equal to 1 minus r to the power minus 4 cos 2 cos square 2 omega minus sine square 2 omega upon, or something will be there, that this will be equal to 1 minus r to the power minus 4. This is cos square a minus sine square a, so this is basically cos 4 omega. Okay, and what we were looking at, what is this quantity? This quantity is S. This quantity is basically real part of this quantity, which means that this thing here is my sigma. Okay, I think I'm making some mistake. Okay, now this thing here belongs to minus 1 to 1. Okay, this thing here belongs to minus 1 to 1, and this thing here is 1 minus cos 4 omega. Now the first thing, that case that we are having, is magnitude of z less than 1, which means that r is less than 1, which means that r to the power minus 4 will be greater than 1. So we have this quantity as 1 minus So this thing here will be less than or equal to 1 minus cos 4 omega, which is equal to I think I'm making some mistake here. So basically what I want to show is when I'm having this magnitude of 1 greater than 1, a magnitude of z greater than 1, it will map to real part of s greater than 0. Okay, so yeah, so this thing I can write as okay. So this thing here belongs to -1 to 1, which means that 1 minus this quantity, this thing will be a positive quantity.
R power minus 4 is there. R power minus 4. That is greater than 1.
Yes,
So 1 minus greater than 1 into the value which is less than 1 or equal to 1.
yes,
So negative we will get.
yes, exactly, correct. So this thing should be less than 0, right? And similarly, when I'm having a plus sign here, that argument will be opposite. That is, if I'm having r greater than 1, then this quantity, this thing, whatever we are having, will give me things which are greater than 0, right? Same argument. So this means that if I'm having magnitude of z greater than 1, the real part of this will be greater than 0, and if magnitude of z is less than 1, then real part of s is less than 0. So what he is saying is, if r is great, this quantity here, r to the power minus 4 is greater than 1, and this thing can take a value. So basically, r to the power minus 4 cos of 4 omega, this thing here is greater than this particular quantity is greater than 1, and this particular quantity is greater than -1. Something is wrong. Can you repeat the thing that you were saying, sir? I lost
Madam,
myself.
you wrote no 1 minus R power minus 4. 1 minus R power minus 4 is greater than 1.
Yes.
Multiplied with some value which is less than or equal to 1.
Hmm.
So definitely this R power minus 4 into cos 4 omega greater than 1.
Yes.
So 1 minus of that is negative.
Yes. Right.
Yeah.
So this we are having. So this quantity here, let
This
me just,
quantity is greater
yeah,
than 1. Yeah.
yeah. So r to the power minus 4. So when
Cos
we are
4.
having r as less than 1, then in that situation, this r to the power minus 4 will be greater than 1, and cos 4 omega.
Limited to 1 maximum. Less than or equal to 1. That is.
So minus r to the power minus 4 cos of omega will be greater
Cos of
than
4
1.
cos of 4
So
omega, madam.
1 minus r to the power minus 4 cos of omega should be greater than 0.
Yeah. Remove minus, madam, for R power minus 4.
Sorry, which r power minus 4?
R power minus 4 into you wrote cos omega, no, madam. In that you remove that minus, negative left side. Yeah. Here cos 4 omega.
No, 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 no. Cos of 4 omega can be less than or equal to 1 only. Okay, I'll get back
Yeah.
to this question in next tutorial. I'm getting confused here. I don't know, I lost my solutions. for this particular option. I'll get back to, I'll visit this thing,
Okay.
this thing, or I'll post the solution in that Google group, whatever is there. I'll post that solution in the Google group. But let us look at the other options. So for the first option, I will send. So let just forget whatever I said. For whatever I know, only option first is correct. I'll send the solutions. Okay, another thing that we are having is, let's see the second option. Second, third, and fourth are easy to understand. So we have s equal to 1 minus z inverse, z to the power minus 2 upon 1 plus z to the power minus 2. So now the mapping from omega to capital Omega, is it 1 to 1? So when do we get omega? So if I have s equal to j omega, so j omega is equal to 1 minus, so I need r, this should map to unit circle. Okay, this should map to unit circle that we want. So then this I can write as e power minus j to omega upon 1 plus e power minus j to omega. This I can write as e power minus j omega outside, inside the bracket it will be e power j omega minus e power minus j omega upon e power minus j omega upon e power j omega minus e power minus j omega, sorry, plus. So this thing here, that is j of omega, is equal to j times 2 times, this thing gets cancelled, sine of omega upon 2 times cos of omega, which is equal to j times tan of omega. Now for a tan function, for this tan, unique range is minus pi by 2 to pi by 2. So basically after pi radians it will start repeating itself. So if you observe carefully, this omega here belongs to minus pi to pi, which means that for two values of omega I will get same value of capital Omega. For example, for a point, let's say, which is here, and a point which is here, so this has 45 degree as angle, and this thing will have 180 degrees plus 45, that is 225 degrees as angle. So for both of these points I'll have tan of omega as 1. Okay, which means that for two values I am getting same value of capital Omega, which means that this is not a 1-1 function. Not a 1-to-1 function. Okay. So the second option was the mapping from small omega to capital Omega is 1-to-1. So this is wrong. Now let us look at the third option. Option 3. And what is option 3? Option 3 is an inverse mapping exists from S to Z. Okay, so what is S given to us? So S is 1 minus Z to the power minus 2 upon 1 plus Z to the power minus 2. This I can write as S times 1 plus Z to the power minus 2, which is equal to 1 minus Z to the power minus 2. So this I can write as S into Z inverse, sorry, Z to the power minus 2 plus Z to the power minus 2, which is equal to 1 minus S. So Z to the power minus 2 will be equal to 1 minus S upon 1 plus S. So Z square will be equal to 1 plus S upon 1 minus S. So when I take Z, this will be under root of 1 plus s upon 1 minus s, but plus minus, which means that due to this quadratic thing here, this will give me two possibilities. Okay, which simply means, so this simply means that inverse mapping does not exist. Okay, so the inverse mapping from S to Z does not exist, which means that this option is also wrong. Okay, and the fourth option is mapping from small omega to capital omega is monotonic. That won't be a case. So again, if we look at this particular thing here, if I'm having two values same, like this and this, so it won't be the case. So basically what is happening is from minus pi by 2 to pi by 2, this thing here, it will go on increasing, then this will go on decreasing like this. So it will increase in this part, and after that this will go on decreasing. So if you look at the tan function plot, you will understand easily what exactly is happening. So it is increasing in this part and then it will go on decreasing like this, and therefore it won't be a monotonic function. Another thing is, for two different values of small omega, if you're getting same value, it can never be a monotonic function. For a monotonic function, one value should be given by only a particular, like a one value of omega should be given by only one value of small omega. Okay, so again this option is wrong. These three options are wrong. This should be correct, but I will send the solution maybe today night or tomorrow morning. I'll upload this on the Google group, and I'll also add a link for this on probably YouTube also. But yeah, it will be there in Google group. I'll add this in Google group. Any questions in these three parts?
No, madam.
Okay. If there are no questions, then let's move on for the fourth question. So the fourth question is a simple one. So it says that an analog filter designer, an analog filter designed using R, L, and C, that is resistor, inductor, and capacitor, is guaranteed to be. So this is multiple answer correct. So it will be rational, it will be causal, it will be stable, and it will be FIR. It is finite impulse response. So which of the following can be true?
First three options, no, madam. First three.
Why will be the third one correct?
Yeah, analog filter must be stable, no, madam.
If you have a second order system, then you may have an unstable system. You'll have that zeta thing, let's say quadratic. You have a transfer function there, you'll have a zeta, then you'll have three regions, one zeta less than one, equal to one, and greater than one. There you will get an unstable system.
Yeah, first option is correct, madam. Rational.
First option is correct. This is correct. You will get a rational system because you will apply that Ohm's law and all those things by taking into, you will get a rational system. Another thing is, the moment you start your system switch on, then only it will give you results. So the moment you apply input, after that it will start giving you your output.
It is
So it is
causal
causal
also.
also. Now, if you are having a rational, like numerator upon denominator kind of system, which you will get every time, and it is an analog system, analog filter, it can't have a finite impulse response. Its impulse response can't have a finite length. So of course this option is wrong. And the stability will depend on how you are connecting the circuit. It will depend. It won't be stable every time. And simply look at the quadratic thing, like, or maybe LRC in series and that kind of circuits, where you will get a two pole filter. So if somehow you get your poles on the right hand side of your S plane, you're gone. And that is totally controlled by that zeta and other things. The second part of this question is, which of the following is true about the realization of an FIR filter? They require less resources for implementation. They are causal. They are always stable. They can be irrational. So they require less resources for implementation. No, IIR filters require less resources for implementation. This was mentioned in the lecture. So this option is wrong. Next thing is they are causal.
Always stable, madam.
Yes. Why can't they be causal?
We have to shift it, then only becomes causal. Shift it to
We
the right side. Yeah.
we have to shift it to the right side, which means that it is possible that if I have a filter which is something like this is -1, 0, 1, 2, something like this. This is also a finite impulse response filter, but still I have a value located here which is at negative value of n, and this makes it non-causal. So these are not causal. Then for stability, what do we have? For stability, this I can write as some k running from my, let's say, k1 to k2 delta n minus k into hk. Something like this we are having. And if you just find absolute sum of this quantity, this will be simply magnitude hk square. So this is h of n. And if you find magnitude square of this, it will be simply magnitude square of each of the hk's, which means that it is always stable. So summation of h of n for n running from minus infinity to infinity, magnitude is equal to summation k running from k1 to k2, magnitude hk's, and this is less than infinity because anyway these are some non like bounded value. So this is a bounded thing. It is absolutely summable, which means that this is stable. And this thing here is of this form, which means that from this thing, I can write h of z as summation k running from k1 to k2 z to the power minus k hk. So this is a rational form with denominator as 1. So a fire filter will always have a rational form, which means that this option is also wrong. So the only option correct is they are always stable. Is it clear?
Madam,
Yes.
so can we say another way? Because all the poles are at the origin. All the poles are inside the unit circle. That's why it is stable.
Yes, you can say that. No, no, no. Wait, wait, wait. If all the poles are inside the unit circle, I don't think so. You can say that. For example, if you look at this filter, which is z to the power 4 plus z to the power 3 plus z to the power 2 plus z to the power 1 plus 1, or anyway let's say z square plus 1, 4z square plus 1. This thing is also an FIR filter which is having one thing here. So this is -1, minus, like this is at -2, then nothing at -1, and at 0 it is -1. This is 4. So this is your FIR filter, and if I need to find its poles are at, so its zeros will be at z equal to 2, z equal to 1, zeros, sorry, plus minus 2, and this is a non-causal thing. It's like this.
Plus or minus 1 by 2. 1 by 2.
No, 1 by 2. But if all your poles are inside unit circle and
Yeah, there is a statement, perfect statement.
see, for stability, you want your unit circle included in the region of convergence.
Yeah, that is one point.
Yeah, it's not saying anything where your poles are.
Okay.
Yeah, I don't think you can say that.
Okay.
Maybe I can find a counter example in the next class. I'll try to do it. Any other questions? So I need to find a counter example for question 4, and I need to give solution for question 3 part A. Okay, yeah. Let's start with, this is a simple question. This is just a match the column part kind of thing. So what it says is I have an S-plane. This is sigma, this is j omega, and I have a Z-plane, and this is my unit circle. This is my unit circle, and we need to see what exactly is happening. So the first thing is left plane. So this is my left plane of S plane, left half plane of S. Okay, and this gets mapped. Where does this get mapped? This gets mapped to interior of the circle. So basically this will get mapped to interior. Next thing is imaginary axis. This imaginary axis j omega gets mapped to unit circle. So this left half plane gets mapped to inside unit circle. This imaginary axis gets mapped to unit circle. And the right half plane, yes sir,
Madam, you say counterclockwise folding?
sorry,
Counterclockwise folding of the S-plane?
what of
Looks
S-plane?
counterclockwise folding. You are folding now.
Huh.
Left, S-plane, you are right hand, left hand side you are folding, right hand side you are folding. That means if it is counterclockwise folding only, it will come
Yes,
inside,
yes, yes, yes,
Yeah, if they are counterclockwise. Thank you.
yes, yes. So basically if you just fold this like this in this
That is
direction, you will get this.
counterclockwise. Counterclockwise.
Yes, correct. This is counterclockwise folded. You can visualize it in that form also. It's right. So right half plane will be mapped to outside the unit circle. This is simple thing. This was covered in class also. Any questions in this part? This comes from bilinear transform and whatever we want to have. There are no questions in this. I'll move on to the next part. So the next question is, choose which of the following filter is realizable. So we looked at certain things for realizable filters, for realizable filters. So the first criteria that we wanted was pass band and stop band cannot be flat. We want some tolerance there. Second point that we saw was we should have non-zero transition band. Okay. And third thing is, since I have a real filter, frequency response this should be even. So these 3 points we need to check in the given 4 options. So let us look at the first option. So if we look at the pass band, this is my pass band. So we are having ripples here. So okay, this is not flat. Okay. Now let us look at the stop band. This stop band here is flat. So here we are having flat stop band. And another issue with this thing is zero transition band. Which means that this thing is not realizable. Now let us look at this particular thing. Now I am having, now here I am having some ripples here, and this is slowly decreasing and slowly decreasing. It's a decaying function like this. This is also a decaying function like this. This is not constant. This is decaying slowly. This is also decaying slowly. And from this part to this part, it is decreasing slowly. There is no sudden transition width, and therefore this option is correct. Okay, so this is decreasing slowly. This is not constant. This is decreasing. Now let us look at the third part, third option. In this, my passband is flat. My stop band is reducing slowly. This is also reducing slowly. I'm having a non-zero transition width, but this is flat. Yes, passband is flat. So this option C is also not possible. And now let us look at this thing. Now if you observe, this is not constant in passband. I'm having transition widths also. This is not constant here as well. So, but the issue is this is not even. This is not even, which means that the filter is not real. So this is not realizable. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the 7th question. So, okay. So which of the following are true for a Butterworth filter? So that is what is being asked to us. So now here I'll just define few notations first. So here omega c is cutoff frequency or some sort of center frequency, which we have seen. Omega p is pass band edge, omega s is stop band edge, and kp is gain in dB in passband Ks is gain in dB in stop band, and we have these four options with us. And what do you mean by gain? So this gain here, K, is basically magnitude of h of omega squared. And yeah, of course, this K should be a function of, or rather, if you can say, this is the maximum gain. This is the maximum gain that you can have. So this is max gain that you can have, and this is min thing that you can have in stop band, and this is max. Sorry, I said ulta. This is minimum gain in passband. This is maximum in stop band. And this gain is actually a function of omega. This is this is in linear scale. And when I have this K, if I convert in dB, this is 10 log to the base 10 of K linear, which means that this is 10 log to the base 10 magnitude of h of omega squared, which is equal to 20 log to the base 10 magnitude of h of omega. Okay, this we have. Right. Now for Butterworth filter, h of omega magnitude square is equal to 1 upon 1 plus omega by omega c to the power 2n. So therefore K will be equal to, or let's say some K of omega will be equal to minus 10 log of 1 plus omega by omega c to the power 2n. Right. Okay, so this we have. So this is to the base 10. So now I can write this as K upon omega upon, or minus upon this, is equal to log to the base 10 1 plus omega by omega c to the power 2n. So I can write this as 10 to the power minus k of omega by 10 is equal to 1 plus omega by omega c to the power 2n. So therefore omega by omega c to the power 2n is equal to 10 to the power minus k of omega by 10 minus 1. So what relation do we have? We have 10 to the power minus k of omega divided by 10 minus 1 is equal to 10 to the power minus, sorry, what am I writing? Omega upon omega c to the power 2n is equal to 10 to the power minus k of omega by 10 minus 1. So this relation we have. So in pass band, we have 10 to the power minus kp by 10 minus 1. Okay, and in pass band, what do we have? We have k of omega greater than kp. Okay, so minus k will be less than minus kp, which means that 10 to the power minus k minus 1 will be less than 10 to the power minus kp minus 1 with by 10 here, and this will be less than or equal to. And if you observe, pass band edge is the least point that we are having for a low pass filter. So this thing here, so that is the minimum gain that we are expecting in my low pass filter, and that thing should occur at my pass band edge. So this should be equal to, using this thing here will be satisfied when my omega will be equal to omega p. So this thing will be omega p upon omega c to the power, oh I'm sorry, something I did wrong, so sorry, there are too many mistakes I'm making. Okay, so in pass band what we are having, okay, in pass band we have my gain as k equal to kp, or let's say it is k greater than or equal to kp, and this kp gain should be greater than or equal to whatever gain we are having at omega p. Okay, so basically this kp should be greater than or equal to k of omega p. Okay, so what I'm trying to say is my expected gain in pass band, minimum gain in pass band is kp, and that gain should be at least equal to the gain that is there at omega p. If it is higher, it's okay. Okay, so then this thing I can write as 10 to the power minus kp by 10 less than or equal to 10 to the power minus k of omega p by 10, and I can have a minus 1 and minus 1 here, and this thing is equal to, from this equation 1, omega p upon omega c to the power 2n. Okay, so 10 to the power so 10 to the power minus kp by 10 minus 1 okay, so this is like this here, it's greater than or equal to omega p upon omega c to the power 2n. What am I writing? I'm so sorry, I'm doing something really bad today. So this is the relation that we are having. Kp is the gain in the pass band, or rather Kp is the gain that we are having in pass band, and this gain should be greater than or equal to whatever gain we are having in k at omega p, which means that 10 to the power minus kp by 10 should be less than or equal to 10 to the power minus k of omega p minus 1 minus 1. Just give me a moment. Is my screen visible? Yeah, it is visible. Okay. So what we are having is at passband, the gain k of omega will be greater than or equal to kp. Okay. So this thing for at passband, I have 10 to the power minus k of omega minus 1 less than or equal to 10 to the power minus kp minus 1. This thing I have. Now in passband, so this omega equal to omega p belongs to passband, which means that my k of omega p should also be greater than or equal to k of p or kp, which means that 10 to the power minus k of omega p minus 1 should be less than or equal to 10 to the power minus kp minus 1, and this thing here is equal to omega p upon omega c. So omega p upon omega c to the power 2n is less than or equal to 10 to the power minus kp minus 1. Yeah, this is correct. Sorry for the mess what I have created. So omega p upon omega c to the power 2n should be less than or equal to 10 to the power minus kp by 10. Now in similar way, in stop band, k of omega should be less than or equal to k of s, and omega s belongs to stop band. Therefore k of omega s should be less than or equal to k of s. So therefore 10 to the power minus k omega s by 10 minus 1 is greater than or equal to 10 to the power minus ks by 10 minus 1. This thing here will be equal to omega s upon omega c to the power 2n, which is greater than or equal to 10 to the power minus ks by 10 minus 1. So omega s upon omega c to the power 2n is greater than or equal to 10 to the power minus ks by 10. Since I made so much mess in this question, let me repeat the entire thing that I have done. So the question is, which of the following is are true for a Butterworth filter of order n and cutoff frequency omega c? So the thing here is the k. We have two notations that I have introduced just now. The first one is kp. So kp is gain in dB. So this is minimum possible gain in passband. And ks is gain in dB in stop band, which is maximum possible gain in stop band. So whatever gain we are having in passband has to be greater than or equal to this kp, and whatever gain we are having in stop band has to be less than or equal to the gain in this particular less than or equal to whatever value this ks takes. Now what do we mean by this gain? So this gain, if I consider linear function in a linear scale, then this will be simply magnitude square of h of omega. Okay, now if I need to take it into decibels, that is dB, when I need to convert it, this is 10 log k linear to the base 10, which simply comes out to be 20 log 10, or basically 10 log 10 to the 10 log mod h of omega square upon to the base 10. Now for Butterworth filter, this magnitude of h of omega square is equal to 1 upon omega by omega c to the power 2n. So this k of omega will be 10 log to the base 10 of this quantity, which is simply minus 10 log of 1 plus omega by omega c to the power 2n to the base 10. So I can take this minus 10 this side. So I have minus k of omega upon 10, which is equal to log to the base 10 1 plus omega by omega c to the power 2n. So if I take 10 to the power on both the sides, so I have 10 to the power minus k of omega by 10, which is equal to 1 plus this quantity. So this particular quantity, which is omega upon omega c to the power 2n, this is equal to 10 to the power minus k of omega by 10 minus 1. And then this is the relation that we have obtained. And if you observe all the options, what we need to find is we need to find relation between this quantity and somehow relate with Kp. So this Kp is the minimum possible gain in passband. So for all omegas or all the capital omegas which are lying in passband, my k of omega, my gain should be at least equal to Kp. So this equation should be satisfied. So now if I take 10 to the power minus k of omega, this inequality shall get reversed, because 10 to the power something is monotonically increasing when my gain is a positive quantity. And similarly, I am having this thing. So 10 into 10 to the power minus k of omega minus 1 will be less than or equal to 10 to the power minus kp minus 1. So this relation will hold true. Now in this omega equal to omega p, this omega p belongs to passband. It's my passband edge. It is a part of passband, and therefore k of omega p. So if I substitute omega equal to omega p in this part, then k of omega p will be greater than or equal to kp. So 10 to the power minus k of omega p minus 1 will be less than or equal to 10 to the power minus kp minus 1. And this quantity here is simply this evaluated at omega equal to omega p. So if I substitute omega equal to omega p in this quantity, I get this thing. So this is omega p by omega c to the power 2n less than or equal to 10 to the power minus kp minus 1. Now similarly, in stop band, this ks is the maximum possible gain that I should get, which means that for all the values of omega, all the values of capital omega, the gain should be less than or equal to this ks. So this k of omega for all the values of omega in stop band should be less than or equal to ks. And for this omega s belongs in stop band, so this equation holds true for omega equal to omega s also. So this is what we get. So 10 to the power minus k of omega s by 10 minus 1 should be greater than or equal to, due to minus sign here, should be greater than or equal to 10 to the power minus ks by 10 minus 1. And again, this quantity here is simply omega s by omega c to the power 2n. This relation we had derived. So now if I summarize, what do I have? I have omega p upon omega c to the power 2n is less than or equal to 10 to the power minus kp by 10 minus 1, and omega s upon omega c to the power 2n is greater than or equal to 10 to the power minus ks by 10 minus 1. Okay, this is the thing that we are having. Any questions in this part? Any queries? Okay. If there are no queries, then let me move on with the 8th question. So this is also a simple question. So we need to find the normalized specs if the sampling frequency is 10 kilohertz, passband edge is 1 kilohertz, and stop band edge is 3 kilohertz. So this is for a low pass filter. So we are given Fs, which is sampling frequency, which is 10 kilohertz, Then we have FP, which is passband edge, which is 1 kilohertz. We have stop band edge, which is 3 kilohertz. And for a given sampling frequency, this omega is given by 2 pi. So basically I'll normalize this hertz frequency with sampling frequency and multiply it by 2 pi just to convert it into angular domain. Okay, this will give me small f, which will vary from minus half to half, because my this fs can be at max 2f. So I'm putting this fs at maximum frequency and that kind of thing. So this is what I'm having. So this is what we are having here. And okay, so using this formula, my omega p will be equal to 2 pi 1 kilohertz upon 3 kilohertz. This comes out to be 10. This comes out to be 0.2 pi, and similarly omega stop will be equal to 2 pi into 3 kilohertz upon 10, which comes out to be 0.6 pi. Any questions? Okay. If there are no questions, then I'll move on to the next part. Yeah. So this is what is given to us is find the order of the Butterworth filter for the following system specifications. Kp is given as minus 1 dB, omega p is given as 4 radians per second, Ks is given as minus 20 dB, and omega s is given as 8 radians per second. Okay, so this is what we are given to us, and we need to somehow figure out the order of our thing. So that we'll find out using these relations that we have obtained. So we have these relations here. Let me just write them down. So first we need to find out order. The two unknown things here are this order and this omega c. We need to find out this order. So now let us try to eliminate this omega c somehow. So the first relation that we have is this omega c upon omega p upon omega s to the power 2n is less than or equal to ten to the power minus kp by 10 minus 1. Okay. So now what I can do is I can take log on both sides. So I can take log on both sides. So what I have is 2n or rather let me just write this in terms of, bring just omega c on one side. So I have omega c to the power 2n is greater than or equal to omega p to the power 2n upon 10 to the power minus kp by 10 minus 1. So this omega c is greater than or equal to omega p upon 10 to the power minus kp by 10 minus 1. So if I take log on both sides, so I have log of omega c, which is greater than or equal to log of omega p minus 1 by 2n into log of 10 to the power minus kp by 10 minus 1, and this comes out. I can just shift this thing on this side. So we have log of omega c upon omega p is greater than or equal to minus 2n log of 10 to the power minus kp by 10 minus 1. So this is the first relationship that we are having. Now another thing that we know is the relationship with respect to omega s. So this we are having. We have this relation. Now let us directly take logarithm on both sides. So we have, or rather what we will do is we will write omega s upon omega c greater than or equal to 10 times minus ks by 10 minus 1 to the power 1 by 2n. So log of omega s upon omega c will be greater than or equal to 1 by 2n log of 10 to the power minus ks by 10 minus 1. Okay, so this we have. Now we need to cancel out omega c from this equation and this equation. Now here omega c is in numerator, here it is in denominator. So if we just add equation 1 and equation 2, what we get is, so adding 1 and 2, we have log of omega c upon omega p plus log of omega s upon omega c is greater than or equal to 1 by 2n log of this quantity, that is 10 to the power minus ks by 10 minus 1 upon 10 to the power minus kp by 10 minus 1, and this thing here will get cancelled, omega c. So we have log of, we add a page, okay. So what we are having is log of omega c upon omega p, sorry, log of omega s upon omega p is greater than or equal to 1 by 2n log of 10 to the power minus ks by 10 minus 1 upon 10 to the power minus kp by 10 minus 1. So therefore this n, I can take this n this side and I can take this thing below this. So this n, which is order, is greater than or equal to log of 10 to the power minus ks by 10 minus 1 upon 10 to the power minus kp by 10 minus 1 divided by log of omega s upon omega p. So in order to meet the current specifications, I should take the value.
Hello, madam. 1 by 2 is there, na? 1 by 2.
Yeah. So in order to meet these specifications, I can set n is equal to C of this quantity, which is log of 10 to the power minus ks by 10 minus 1 upon 10 to the power minus kp by 10 minus 1 divided by 2 times log of omega s by omega p. Seal of this. So basically, in order to meet the current specifications with minimum resources, I'll take the least integer value of n, which will satisfy this particular quantity. Now we know this formula for order, which we have just derived. So now what we have is, what is given to us is kp is minus 1 dB, omega p is 4 radians per second, ks is minus 20 dB, and omega s is 8 radian per second. Okay, so now if I substitute this in this n thing, n's equation, so this comes out to be log of 10 to the power minus ks. So ks is 20, minus 20, so minus of minus 20 is 20 by 10, which is 2 minus 1 upon 10 to the power minus kp by 10. So minus kp is 1 dB, so this will be minus of minus, so this will be 0.1 minus 1 divided by 2 times log of omega s is 8 radians per second and omega p is 4 radians per second, and C log this. So if you use your calculators, this comes out to be 4.289 and its seal, and the first integer or the integer greater than or equal to this quantity is 5. So the order is n equal to 5. Is this clear? Is this question clear? Any queries in this question? You can directly memorize this formula for a low pass filter. This formula which I have written here, you can memorize it, and whenever you are given specifications in this form, you can simply substitute it in this in the given equation. Any questions? Yes, sir.
Madam. Hello, madam.
Yeah, please ask.
You are putting Ks and Kp,
Huh.
and somewhere we are seeing delta 1 and delta 2 as passband tolerance and stopband tolerance. Both
Yes,
are
sir.
equal.
No.
Both are.
No.
This is different.
Yes. I'll tell you how.
Oh, okay.
Yeah. Thank you for that question.
Okay.
Yeah. So this is my omega axis, and let's say I'll plot mod of h of omega square. Okay. So now this is my filter, which will go something like this. Okay, this is not symmetric. This is something like this. This will go and then this will go and then reduce like this. Okay. Now let's say this, what we want is we want 1. Ideally we want something like this. Like this is my ideal filter. This is 1, which means that this thing here and this thing here is my omega. Sorry. So this is what we wanted. This is what we wanted. This was 1. But what we are doing is we are allowing this much thing in my passband. This much. Okay. So this is 1 plus delta 1 or delta p and 1 minus delta p. Right. So this delta p is passband tolerance. But let's say I have this thing here. This thing here is my passband, let's say. So the minimum gain that I need in passband is kp. So this will be my value of 10 log of mod of h of omega square. So this variation this variation will be given to me by tolerance. However, the minimum value of passband that I expect is given by this gain Kp. And similarly, I can have a stop band here and I can have a tolerance here. And then I can have a maximum possible gain that I can have in my stop band. Yes, sir.
SR always uses delta 1, delta 2, but you are telling in terms of gain.
So
It
this is a question from last year's assignment. That's
okay,
why I
but
purposely took this question so that you people don't get confused if you see suddenly this kind of structure in assignment.
questions are on delta 1, delta 2 only, but you are telling about the gain. We are totally confused.
Sir, the delta thing is discussed in lecture. You have equations for that, and when you will see these kind of specifications will be there in upcoming questions. It will be there in upcoming assignments.
Yes, yes. Okay, madam.
You can see this is last year's assignment. They have asked it in this assignments, means definitely they may ask the similar thing in final and other things because same videos are repeated.
Okay, madam, I'll agree. But why sir didn't focus on that KP and KS while sir is discussing with us? We can see his discussion only. We can't see the old assignments, no?
Sir, the Butterworth filter designing is not yet complete. So maybe in upcoming week thing he will discuss this. This will be discussed. But since they asked such questions in previous assignments, I purposely took it.
Okay, madam.
Any other questions? Yes, sir.
Madam, we are not getting old assignments anywhere. We are unable to get the old assignment.
You won't get old assignments. I am taking questions from old assignments. All the questions. That's
If
how
that
you are
bank,
getting.
if that question bank is there, no, we can prepare well.
I am giving you questions from last year's assignment. These are
No,
last year's
previous
assignment
also,
questions.
this course was taken number of times, no, madam. If those questions are available somewhere, we can
So those are
prepare
not
well now.
available to me also.
Okay, madam.
These are the only questions that are available to me. So whatever is available to me, I am giving you all.
Okay.
Yeah. Maybe you can try searching on Google. I didn't try that. Might be available. I'll also see if it is available. But yeah, this is the only access that is given to me. Any other questions? But yeah, I think you can solve few filter designing questions which are there in Procus book. Procus has good amount of questions on Butterworth filter designing. And yeah, those people use this KP and KS kind of specifications. So maybe you can look into that and solve questions in that. It has good amount of questions, solved and unsolved both. It will be helpful. Okay. So now let me move on to the last question. So for this question says that for the previous, yes sir. Yes sir, please ask your question. Sir, I'm unable to hear you. Can you please unmute yourself and speak?
Sorry. I have unmuted. Sorry.
Yeah, yeah.
Madam, you give a ceiling symbol, no?
Yeah.
Ceiling means correction, no truncation, no?
No. Ceiling doesn't mean truncation.
It
Ceiling
is correct
means
correction.
no.
Correction means next higher number.
Yes, next
Oh,
higher integer.
next higher integer. That's all.
Yeah,
It's not truncation. Okay, thank you.
it's not truncation. It's next higher. Okay. Okay. So, okay, so let's start with the last question. So it says that for the previous question, which of the following are allowed cutoff frequencies? Or basically, instead of saying this, what is the range of frequencies that omega c can take? Okay, so now again I will get back to the good old relations that we are having. So we had this omega p upon omega c to the power 2n less than or equal to 10 to the power minus kp by 10 minus 1. So this I can write as omega c greater than or equal to, or rather omega c to the power 2n greater than or equal to omega p to the power 2n upon 10 to the power minus kp by 10 minus 1, which means that omega c is greater than or equal to omega p upon 10 to the power minus kp by 10 minus 1. So this is the first relation that I am having, that omega c is greater than or equal to omega p upon to the power 10 to the power minus kp by 10 minus 1 to the power 1 by 2n. Okay, now we have another relation where omega s upon omega c to the power 2n is greater than or equal to 10 to the power minus ks by 10 minus 1. So now I have omega c to the power 2n less than or equal to omega s to the power 2n upon 10 to the power minus ks by 10 minus 1. So this omega c is less than or equal to omega s upon 10 to the power minus ks by 10 minus 1 whole to the power 1 by 2n. So this is the second equation that I am having. So from equation 1 and equation 2, so from 1 and 2, this omega c is less than or equal to this quantity, that is omega s upon 10 to the power minus ks by 10 minus 1 to the power 1 by 2n, and this is greater than or equal to omega p upon 10 to the power minus kp by 10 minus 1. Now this ks, in previous question this ks was minus 20 dB, kp was minus 1 dB, omega s was 8 radians per second, and omega p was 4 radian per second. So if we substitute these values in above equation, what we get is, after using calculators and all, we have this quantity as 4.5787 less than or equal to omega c less than or equal to 5.0527, this thing here. Okay, so this omega c will belong in the range of 4.5787 to 5.0527. So anywhere in this range, any omega c in this given range I can take to design my filter. Okay, any questions? Any questions in this part? This was the last thing that I wanted to cover today. Yeah, by today or by tomorrow morning, I'll upload the solution of question 3, part A. Why it is true. I'll do that. And yeah, that I'll do. And sorry for whatever mess I created today while solving questions. Extremely sorry. If you have any queries in those parts or any question for that matter in today's tutorial, please let me know. Yeah, and one more thing, I think, sir, you had posted, Murthy sir, I think you had posted a question for multiple polls on the portal. Am I right? If I have understood your question properly, then you are saying that I have discussed a question where for the for getting an approximate output equation where I just have one pole, right?
Madam, it is not about that question. When we are solving some other question, we got multiple poles.
So I had used one pole there. So in case you have another question where there are multiple poles at the same location, then how to do that? Is it correct?
Yeah.
I have understood it correctly, right?
Okay.
Like your question, it's correct, right?
Correct.
So basically what you're saying is, so you have, what I have discussed was of this form, 1 minus az to the power minus 1. And suppose you have something like this, 1 upon 1 minus az inverse to the power, let's say k. Right, something like this you're having.
Yes.
Yeah. So for this thing, now if you remember, I'd like you to recall this property. So if I'm having x of n, having z transform as x of z, then n times x of n will have a z transform minus d dz x of z and with a z multiplied here, right? We have this thing, right? So if I have n into x of n, so just look at this. Let's consider only this thing here. This thing, for this thing, let's say this is x of z. So if I have this, then d dz of x of z will be equal to minus 1 upon 1 minus az inverse to the power minus 2 into minus a into minus 1 into z to the power minus 2, right? So this will be minus a z to the power minus 2 upon 1 minus a z inverse to the power minus 2, right? You have something like this. Then you have,
It's plus 2, madam. Plus 2.
why plus 2?
Denominator. To the power plus 2.
So minus z into d dz x of z will be equal to az inverse upon 1 minus az inverse to the power 2. So now if you observe carefully, when I am having a square term here, like I have two repeated poles here, so that will correspond to multiplication by n here. Am I correct? You forget about this numerator. Anyway, we are doing some c upon something d, some kind of approximate kind of thing. So if you just focus on this denominator, then I am having this denominator here. So I'll have a multiplication by n. So if I have k repeated poles, then you can write it as a to the power, sorry, a into n to the power k minus 1 plus b, sorry, like this you can write. So what I'm trying to say is, this is covered in lecture. As far as I remember, this was covered in lecture. So if it is of the form So if you have pole A with multiplicity 2, you have pole B with multiplicity 3, you have pole C with multiplicity 1, then what you can do is, so this is pole A, pole B, and pole C. Or okay, let's say I have a pole half with multiplicity 2, I have a pole 3 with multiplicity 1, and I have pole 1 as 1 by 4 as multiplicity 1. So I can write this y of n as, you have two poles, right? So for one pole you have 1 by 2 to the power n into un, but for two poles you will have to multiply it by n, and there will be some constant a which you need to find out. Similarly, for 1 by 3 it will be n square into 1 by 3 to the power n u of n plus c into n cube, c into, it is just of a multiplicity 1, so 1 by 4 to the power n un. So just be careful, this is just an approximate equation, so that's why we are not caring about whatever term we are getting here. So this is how we'll solve it. Does it answer your question, sir?
Madam,
Yes, madam.
Okay, thanks.
madam, I had doubt, madam. I think you wrote, suppose at 1 by 2, two poles are there. Then I think we have to write A into n plus 1. A into n plus 1, because there will be A into half power n v of n, one possibility, other one is A into n into half power n v of n. So we have to write n plus 1.
I'm not getting what you're saying, sir.
Here A is common, madam, common factor A that we have to get.
Huh.
So then half power n v of n will be having one term multiplied with A, another term multiplied with A into n. So no, madam. A into n plus 1, what I am telling. A into n plus 1.
A into n
It
plus
is
1
not,
into half to the
yeah,
power n u of n.
power
Why are you
n v
having
of
this
n.
n plus 1 here?
Because here one term without n, another term with n, both are possible, no, madam.
Huh, but how do you know that both of them will have same coefficients? They can have different also, na? A may not be
Because
equal to B.
they will be having same coefficient, madam. I think it is there in standard books also, I think.
Okay, then follow it.
Yeah.
But if I remember carefully, you have to multiply by n somehow, and you need to compensate it. Or in most general thing, what you can do is just have all of these things different and then solve multiple equations that you're getting.
Okay.
Yeah, I'll look into it. But it's there in lecture. I have that.
Okay.
Any other questions? So the whole idea of doing that kind of thing is this thing. So in more general sense, you can write it something like this. This is the form in which you should get your output. Even when
Okay,
you are
madam. So you
doing
are
your
saying that
partial
different.
fractions thing, na? Like if you have something like z inverse upon 1 minus 1 by 4 z to the power minus 2, you write this as b plus c z inverse upon like 1 minus 1 by 4 z to the power minus 2, and then you try to find out. So in that also you get something like this. Maybe I'll check once whether a
Okay.
should be equal to b, but this is the form in which you should get your equation.
Okay.
Yeah,
Generalized form. Okay.
generalized form. This is the generalized form in which you should get your expression.
Okay. Thank you, madam.
And it may be the case where a and b are not same. It might be the case.
Okay.
I feel so.
Only thing is we need number of equations
Yes, yes. You will
to
need
solve
number
it.
of equations for this.
Yeah. Okay.
Yeah. We'll need at least 1, 2, 3, 4, 5, 6 equations to find it. Any other questions? If you have any other questions, then let me know. Otherwise, you are free to leave the meeting. And again, sorry for today's miss. I'll upload the solution for part 3. Thank you for attending today's session.